কাছাকাছি বসছে। ঠিক আছে, ঠিক আছে। তাদের মানে পয়েন্টে যা 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 দেখেন একটা Yes. So thank you for introduction and okay, so I'm from Shibpur beautiful campus and you are welcome here. If you want to visit here, so it's getting nearby and inside the other and see teacher here. So you can enjoy reading it. Now my topic is very simple and it is there are some pictures only. So if you don't understand, just raise your hand and stop. So my topic is my topic is Bose-Einstein condensation. Uh, Metropolis analysis. In these topics, first I review some of the excellent and properties and the effect of in the Bose-Einstein condensate. Then I will explain how can we apply Metropolis algorithm to solve the problem. Now, Bose-Einstein condensation it is proposed by Einstein based on the Bose statistics. So this Bose, it was in the graduated from this institute. So this topic is so this topic emotionally matters. Phenomenon is emotionally attached with this institute, and it is the 100 year of opposed of Bose-Einstein condensation. So this is relevant in this sense, and it is achieved in Arnold atomic system in 1995, 70 years after the proposal. And there are people particularly he did for the sodium atom and their element and Cornell did it for rubidium 87 atom. And what is this element like this? This is the velocity distribution term. This is velocity distribution. Consider this is x-axis of velocity, velocity x component of velocity, y component velocity, and z-axis is the height is the number of particles with velocity. Number of particles as function of velocity. So at high temperature, this is high temperature and this is low temperature. At high temperature, velocity is distributed as per Maxwell's distribution law. So it's almost Gaussian. And if we decrease the temperature, after a certain temperature called critical temperature, almost all the particles condense in the zero velocities. Not exactly Gaussian, but if we make it very high temperature, it's almost Gaussian. Actually, it's follow Bose statistics. Not at all. By some. Ah. So, not exactly Gaussian, but I mean, almost nature. Okay. There is some tail also. So, and what is that? Below a certain temperature, almost all the particles condense to zero velocity. So, this effect is called Bose-Einstein condensate. And another mechanism, why this mechanism is like that, is quantum phenomena. So, lambda is the wavelength. De Broglie wavelength is made by T is the momentum. At high temperature, temperature is very high, lambda is very small, and the particles behave as classical particles. So they randomly move here and there. There is no overlap. And if we reduce the temperature, it will become high. It will become high, and if we reduce further temperature, waves are superposing on each other. Waves are superposing on each other. And below certain temperature, all the waves superpose and form a single beak. This is the condensate. This is the condensate. This is the super. Compare this for quantum superparticles. We have a single particle or single wave. Why it is so hard to achieve? Because it took 70 years. Why? Because if we see any undergraduate conditional mechanics book, you can see critical temperature for non-interacting Bose. Critical temperature is in the density of the condensate or density of the particle, and theta function, theta 3 by 2, and this by h square by k is the mass of particles and k is the probability. Now, if we reduce the temperature, what will systems become solid or liquid or solid. To make it gas, the density should not be less than 10 to 20 per meter cube. Density should not be less than 10 to 20 per meter. And we put n equal to 10 to 20 and put if we consider the rubidium atom, mass of rubidium atom, then EC become around 100 nanometer. So this is the problem of achieving Bose-Einstein condensate. Because you have to reach, if we consider physical atoms, you have to reach nanometer temperature. And why it is from how to reach nanometer temperature? First take gas of alkali atoms in a magneto-optical trapping at milligauge. So milligauge is acidic. We can use liquid helium, then adiabatic demagnetization cooling. So milligauge is accessible for long time. But microfilming and nanometer beams are neat. So what means magneto-optical trapping? You cannot keep these atoms in a physical container, because if you put the atoms in physical container has some temperature, so atoms will get heated. So temperature will raise, but not due to the interaction between container and the atom. That's why we have to use magneto-optical trap. Then use laser cooling. So using laser cooling, you can reach to microcooling. What is this? Also, this is an atom with energy level. This is the atomic energy frequency, and this is a photon. So photon is coming this way, and atom is at this. and frequency of photon is less than the frequency of photon is less than the atomic frequency. So the photon will not interact with the atom and will go away. Now, if the atom, this is the atom, if the atom and photon are coming toward each other, then into the Doppler effect, so frequency become higher, and for a certain situation, it may coincide with the atomic frequency. Then it will absorb the photon, and velocity of the atom will be reduced. Velocity of the atom will be reduced. And atom again release the photon in random direction. So after some times, the temperature of the system will be reduced. This way you can reach to micro temperature, but you have to reach nano temperature. So we can use evaporative cooling. So what is evaporative cooling? Just evaporate the higher energy particles. So consider this is the trapping of atom. Reduce the trapping height. So high energy particle will be removed. And to reduce further, reduce the atom confinement potential and keep the only low energy particle. So average energy will be this. So temperature will be. So we get nanometer. And I'm to randomly list some of the properties or actually features of the system. Velocity of light is 3 to 10 to the power 8 meter per second in 3 space. But if we consider the velocity inside the condensate, velocity becomes 17 meter per second. So you can reach fast. Your speed may be faster than light. Height for it. So we can. Okay. So here we have two condensates. This is one condensate. This is the density of one condensate. This is density of another condensate. And in the superpole, they form a interference. And this is the experimental and this is the clip. And this is the phase metal. BEC, a superfluid gas. Superfluidity of helium 4 was liquid and it was observed in 1937 by Captain Allen and by Graf, and it was explained by Lander. Now, superfluid gas. This is in here, superfluid gas. So, gas superfluidity you can understand by the absence of viscosity. And if it is superfluid gas, so that can be understood by rotation. Consider classical fluid. We are considered classical fluid. If we rotate, all the liquid will be rotated together. And if you consider superfluid, take a spoon and rotate it. Your spoon will move, but you do not move. But if you move your spoon rapidly, then there will be vortex. Not a single vortex, many vortex. There will be vortex, not a single vortex, many vortex. And the vortex are arranged in triangular pattern. Lightest liquid. So consider potassium atom, and in BC phase we can liquefy it. Its density is 10 to the power 14 atom per cc, which is million times less density than the air. So this is the lightest liquid. And supersonic. What is supersonic? Supersonic is that there is a pattern of crystalline pattern. At the same time, It has superfluidity. Phase follow the superfluidity nature. There are density follow the crystalline nature, and phase follow the superfluid nature. So this is the experimental finding. So this is Dwipesh atom. This is dipolar atom. So this atom has two type of interaction. One is contact interaction, another is long range dipolar interaction. Dipolar interaction, dipolar interaction is long range, and you can arrange atoms such that dipolar interaction sometimes attack, and in a particular situation they repulse. So here they use the dipolar atom in such a way that they are attractive, but contact interaction is repulsive. So if we remove the dipolar contact interaction and allow the dipolar interaction peaks, then at a particular temperature and interaction parameter, the fluid becomes supersonic. So it's a density. It is not the atom. This is the collection of atoms. In this point, because we don't have single atom entity. So identity. So they collapse and form a big atom. And this big atom or condensate, so here and there and there, so arrange themselves to form a supersonic. And there are many applications. One of these is the quantum computer. There is a proposal of quantum computer. So yeah, there you can make a QB. So you have a very low temperature condensate and apply some magnetic field and create a giant atom called a deep particle. So you cannot make at a single point. You cannot make more than one deep particle due to the Coulomb repulsion. And make two Rydberg atom. These two Rydberg atom, they form a quantum computer. But problem is that it requires very low temperature and requires magnetic optical confinement. And it is not robust, it is fragile. Lifetime is millisecond to few seconds. And size of the condensate is micrometer. So that are the restriction. We cannot make the quantum computer active, but there is future scope. For these people, as it has tremendous aspect of application, people set up cold atomic lab in space. 2017, after successful of first phase, they try to establish a second one, at 23, and NASA also. And what they achieved, actually, at present we don't have new physics from this lab, but we have reached some other things. Their lifetimes has been reached to 6 minutes, from second to minute, 6 minutes. And size also they produce bigger size, and their measurement more precise. But up to this point, there is no new physics, but sophisticated. Now come to theoretical point. So theoretical point, Bose atom are trapped. So Hamiltonian is kinetic energy. This is kinetic energy minus. There is some mistake. Minus e square means minus a square by twice a lambda square. This is kinetic energy. This is trapping potential. This is interaction between atoms. So Hamiltonian has three parts: kinetic energy, confinement potential, interaction. So most of this confinement potential is harmonic confinement potential. Half in omega square, x square, y square, z square. And interaction, if we consider neutral Bose atom, and density is very small, density is very less, and temperature is also very less. So in this temperature and density, there are possibility of coming three atoms together at the same time is very less. So forget about the three body and aeroplane interaction. Consider only two body interaction. And consider the model potential, simple model potential, which is called a hardcore potential. When two atoms come together, potential will be used so that they cannot be come closer. And if they part apart, their potential is cheap. Now, you can write Hamiltonian, as we have Hamiltonian, you can write Schrodinger equation. I is for density is equal to H. Or H is and psi is the function of 3n plus 1 number of variables. So this is the things we have to solve. This is our Schrodinger equation. So usually the partial differential equation, usually to solve partial differential equation, what we do, we apply method of separation of variables. But method of separation of variables is not applicable here due to this correlation term. So method of separation of variables is not applicable. And it's different methods. There are one method, this is called density functional method to solve that equation, but density functional method is applicable for periodic systems, exactly periodic systems, crystal and solid at zero temperature. And there are many softwares using this density functional method. Problem is that it is not good for mesoscopic, nanoscopic, and system at finite temperature. As our system is mesoscopic, so we cannot apply density function. So we can apply a variational principle. We can apply variational principle. In variational principle, what is the starting point? Starting point is the case or choice of wave function. In the variational principle, the starting point is case or choice of wave function. How to choice? To choice, we have to have knowledge about the wave function. Consider many particle systems. Consider n number of identical particles. N number of identical particles. Now, if we interchange two particles, I particle and Z particle, system will remain identical. But wave function can change. Wave function is not physical quantity. So phase of the wave function may be changed. So if I change two particles, I position and Z particle position, so wave function that may be phase vector. This is P. So if P is plus 1, it is called boson. If P is minus 1, it is called particle. There are mostly two kind of particles, and there are some other kind of also, so these are called animals, which is not available in this space, but in some strange medium also. Now consider study interacting system. First we analyze the non-interacting system. Non-interacting system is this part issue. This part is not here. So Hamiltonian can be written as sum over A side, single particle Hamiltonian. Hamiltonian can be written as combination of single particle Hamiltonian. And H psi n equal to epsilon psi. This is the IIEST. And if it is Fermion, the wave function can be expressed in terms of single particle wave function. This is called Slater determinant. And if it is boson, boson is symmetric wave function, and determinant is asymmetric. To make this symmetry, in determinant quantum positive and negative, positive, negative. So put all the negative sign by positive. So make all the terms positive. So this is the boson. Is contradiction or normalization? Okay, I am not considering normalization because okay, it is not normalized. To normalize, there will be a factor 1 by root over of n. Factorial, root over of factorial. To normalize this function, wave function, we have to multiply 1 by root over of factorial. Provided single particle wave function is also normalized. Now, if we consider interacting system. So for interacting system, Hamiltonian cannot be written as a combination of single particle Hamiltonian. That's the problem. The wave function cannot be expressed in terms of single particular values. Then variation of that. And how it's called? Consider non-interacting system. Consider non-interactive system of the same system. Same Hamiltonian drop the interaction part. And there's the drop the interaction and see the nature of the wave function. Then choose a suitable wave function of the interacting system with some parameter alpha. And variation principle is that for x, I can change the parameter for energy will be minimum for exact wave function. For Kumar wave function, energy will be minimum. Energy will be minimum. So we just find E alpha is function of alpha and see where we are getting minimum. So we have to find. Okay, first is the Hamiltonian wave function. Then the Hamiltonian, which is for simplicity, we just consider simplest confinement potential of square x equals to this. So wave function guessing is this. Gi is the minus alpha. This alpha is the parameter. X square y square z square. And this mi is called the Jastrow factor. This includes the interaction part. This Jastrow factor includes the interaction part. So this is not included interaction part. This part included interaction part. So 1 minus A is the interaction. You can remember we have considered the potential. This potential, if two particles separated more than potential A, the wave function will be potential will be 0. If two particles closer than A, potential will be infinite. So two particles cannot be come closer than A. So if that's why A we choose this way. So if A R is less than A, wave function is 0. So wave function will be collapse. And if Ri is greater than A, there will be wave function. So this confirm two particles cannot be closer than A and also include the interaction. The basic function of yes, I think we I don't have some explained on this side. You are not people permanent. That means you bigger than the waves. So I am considering this one, but I am very bigger. Okay, so hydrophorism actually Bose-Einstein condensation can be considered we studied in 3 ways. Theoretical approach or micro approach in gross frequency equation. This is the simple equation and this is the so I feel this technique because article approximation has some complicated things and there is a if you consider IIEST particular and it will be more complicated, very difficult to understand. But this then possibility of that is very realistic. And that will be more complicated and this is actually more complicated. So there is another I'm just discussing this. Now this is our I think those who have completed asked course of quantum physics they can understand. Otherwise it is very difficult and so on for them. So this is the okay. So here we don't need quantum mechanics. This is the term used. This is n number of variables x or x2. N number of variables psi star, y star. Now we may apply Simpson-Monta method. You know Simpson-Monta method. In this method, what we do, we just take the region of the integration and divide this region by some finite points, 5 division, consider 100. And if it is real number of variables are there, we have to consider 10 to the power real numbers. So we have to consider 10 to the power real number of points. Now, if the speed of computer is gigahertz, so minimum time step part step calculation is nanosecond. Now, if you consider n equal to 50, so our calculation time will be 10 to the power 150 nanosecond. 10 to the power 150 nanosecond. And which is, if we consider that will be 10 to the power around 300 years. And if you consider apply other computers, it requires 10 to the power 280 years. The computers in parallel. Parallel. So it is not possible to do state forward. It is not possible to do state forward. This is the problem. So our job is to find this. This is our motivation. So state forward taking is not happening. So consider instead of finite difference method, we use random sampling. Random sampling. Random sampling method is very popular and applicable in many spaces, many problems, except some few problems like prediction of election result or something real more real life problem. But it is very predictable. The result of this method is very useful. Can grow of bacteria, virus, spread of virus. Also the solution of quantum mechanical problem, and there are many more. It is very efficient. The method is that instead of considering all the points, choose some of the points. The basic point is that, like when you predicting the result of election, we don't consider all the people, all the voters. So choose some of the voters. Like this, we have to consider this number. We don't need to consider this number of points. We'll choose some of the points. We'll choose some of the points out of this. We'll not consider all these points. We'll choose some of the points out of this. And how to choose some of the points, that is important. And this is the problem. Let's say n is the function. I have integrative, and I will make this integration convolution integration is like this rho by rho. And I am calling this rho is a probability distributive function. Rho is a distributive function. So this is the position distribution function. So I am calling it G, and the integration, and if the required distribution function, then G the integration of F becomes somewhat of G R, and M is the number of points we have to get. M is the number of points out of 10 to the power that number, big number. Out of big number, we have to get sum of the points. This number is M. So then it becomes summation of function at that point, and error is of the order of 1 by rho. So this is called an example given on the dimension of the problem, and this over distribution known as important sample. This choice of position is called this is the name. So we choose, let's say R0, R1. This R0 is the R is not the single particular position. This is R is n number of particular position. Okay, all position are combined. I am calling it capital R. Combination of all small r. So instead of choosing this, I will choose. This is called Metropolis method, Markovian method. Choice of Ri depends only on the previous point. Okay, when you choose Ri, it depends only on Ri minus 1 point. It only just previous point. It is called sometimes it is called a random walk problem. Okay, so it is associated with random walk problem. And this choice is not unique. This choice is not completely unique. It may be different. So how we choose consider this is Ri position, and now I have to choose Ri plus 1 position. This is small r1, small r2, small r3, small r3, combination of all these. This is capital R. Now I have to choose next position. Draw a sphere or circle around this point. And oh, sorry. Uh, choose randomly a point inside this circle. Completely random. Choose completely randomly points inside the circle. And so this is the new. So these new points, is it Ri plus 1? So this is Ri. This black part is Ri. And these new points, is it Ri plus 1? So that is depends on the distributive answer. So this is the trial position, this is the Ri position. If rho RT by Ri is less than 1, accept it and go for the next position. And if it is not, then reject it and again choose randomly and compare it. This way you can choose the point. And how to start from RT? So this is the point Ri2, point 2 into 3, but how to consider first one? How to choose first position? So choose create random points in the configuration space randomly and run the Macrobian process sufficient number of iteration and consider this is the acceptable. Also, how do you set the convert this? Okay, that depends on the experience. Okay, so of the order, actually error is of the order of 1 by root a, so it will be of the order of milli-order. But if we consider R0 just a few thousand pieces, because R0 is a random point and Cooper random, the Cooper random dimension, it is called normalization. So we don't need any accuracy because for accuracy we don't need any 99.99 accuracy. So 1% accuracy is sufficient to start. It's just a random position. So it is very so okay. So this way we can start from choosing the position. And this is the Bayesian method. So we have to find the energy. So it is psi star H psi by psi star. We multiply psi by psi. Then we will have this psi this H psi by psi. H psi by psi. I'm calling it E. And I'm calling psi square by normalization. Normalization psi square, I'm calling it the probability distribution function. Within distribution function, so distribution function should be associated with the problem. And wave function is a distributive function, probability function. So we can consider this wave function square as the probability distribution. And as this is not unique, so we can find several times. So several times we can find the energy several times and we can make it and take the average to make it statistical average. Okay. And And we have to, and we can remember our wave function was multiple of two function. This is the calculation technique how to handle the derivative of two function. That is just quick line calculation. And this is the energy calculation. So you can find the energy of the system. 40.5. This is the red points are Gauss-Peterson equation, solution of Gauss-Peterson equations, and these black points are variational model.
What is the chemical constraint? What is the chemical constraint in A by N?
Yeah, H cross omega 0 energy expressed in terms of, actually there is a confinement. So our energy is still considered as H cross omega 0. Omega 0 is the confinement frequency. And A0 is the confinement length. When you solve simple harmonic motion, your L equal to root over of H cross, what is the point? There is omega is relative. Okay, so there is a length scale. Your harmonic oscillator problem, you write e to the minus x square by 2l square. That L is the length. That is it. Yeah, I am telling it. Now this is for zero temperature. We consider finite temperature. We consider finite temperature at T or temperature. So what is the when we study? So average value of any expectation value of any operator is 1 by z plus rho operator. Where rho is equal to density matrix. Rho is density matrix, it is equal to minus beta x. Beta is the temperature and H is the Hamiltonian. H is our Hamiltonian. And Z is the case of rho and psi I are the eigenstate and I is the eigenenergy. So this problem is straightforward as people, but problem is that if you know the energy, eigenstate and eigenfunction. So if you know the eigenvalue and eigenfunction, then it's easy to do. But here the problem is that we don't know eigenvalue and eigenfunction. So how to proceed? We have to evaluate path integral quantifier. So path integral, if you care about path integral, what is the first impression? Path integral. Finite theory. So finite path integral formulas. So this is very well known. So this is the covariant. So xi to xa. Xi to I, initial position to final. What is the probability of going from this point to that point? This is called covariant. And this is basically xa. This is e to the power minus I h pf minus pi by h square. H. And okay, so
But yes, density matrix is not generally diagonal. If you have the interaction, you answer.
okay.
If the interaction is negative, then it is diagonal. The Hamiltonians are separated.
So if Hamiltonians are separate, then it is exactly diagonal.
Then diagonal.
If it is diagonal, then we can do exactly.
And then if you look at the interaction, you answer. So we are not even diagonal.
Okay. So thank you for the question. Pointing my mistake. Sorry. I have no this. So okay. So this is not diagonalized. So it should be I and G. It should be I and G. And the finite path integration. So if it is classical mechanics, the path is unique. If it is classical mechanics, path is unique. And if it is quantum mechanics, in quantum mechanics everything is probabilistic. So it can move from here to there, this way, that way, this way. There are infinite possibilities. There are infinite possibilities. You have to include all these possibilities. This is the final formula. And if we do some calculations, I have not shown here. So small step and different part into it. So it can be written as this dt means dx1, dx2, dx3. This capital D means dx1, dx2, dx3, and in principle infinite. And this s is the action. S is called action, which is integration L dt. P1 to Pi to Pf, and this is kinetic energy minus potential. Now, this is the final particle concept. Now, come to our problem. Oh, so I can discretize this problem. So consider n number of parts, and this time can be discretized. So, in numerical problem, I cannot consider infinite. I have to consider finite. So consider n number of parts, and in numerical you have to, there is integration of over time. So the time also discretize. So delta t is the small step of time. So this is the discretized. Now come to our z is equal to trace is equal minus beta x, which is equal to if we consider space. And it will become minus h tau by h square. Okay, so I should consider x1 and x2. They are defined. Actually, it is not diagonal. No, it's diagonal. But our component result will be same. Argument result will be same. But I should consider x1 and x2 different position. So it is not as it is not diagonal. I have to this for this. So it is exactly similar if you are I minus I is t by h square. Then it is minus I tau by h square. I am just putting this beta as tau. Just to make this similar loop, to make it similar loop. So except they are the same thing except to xi. So except to xi, it is minus b minus h. I is not there. Except I. These two are exactly similar. Except I, these two are exactly similar. This is final formula. It is minus I is t by h square. It is minus I tau by h. Except I. And if we use the same technique, we can this here as I is not here, then it will be minus I s by h cross. Similarly. I is by h square there goes plus and it will be minus. I is not there, and this case is not Lagrangian. Here corresponding action, equivalent action is not indication of Lagrangian, it is rather indication of Hamilton.
What is the observable there in the trace relation? In the trace relation, t power minus h beta is your
partition function.
Is your observable?
Partition function is not observable. Partition function is not observable. If we find partition function,
it's an operator. H.
No, partition function is not operator. This is a number.
Trace of some kind.
It is a number.
না যদি ম্যাট্রিক্স হয় তাহলে তো অপারেটরই পড়ে
না you trace calculate করে নি
না আমি জাস্ট ট্রেসের ভেতরের আর্গুমেন্টটা বলছি
that
is a matrix okay that is an operator you need to do the trace you need the state of the system to make the trace.
Yes, that's why, but that is not doable here. That's why we are going this way. So we are not straightforwardly calculating it.
But that depends on the representations you are using. If your representative is defined in some basics, then it is automatically
because we don't know the proper basis, we don't know the eigenvalue eigenfunction. That is the problem. That's why we are bypassing some other. So this is the path integral. It's called numerically, and we cannot do it analytically. We should go for numerically. Okay. So, okay. After if we have Z, then we can calculate the physical quantity. From Z, we can start physical quantity. So this is our, and this S is our, this S is our equivalent S is our integration of Hamiltonian, not the Lagrangian. So this transformation because of the presence of I. And here actually, I will say here actually over. So this R applied. It should be R applied, defined position. And observe statistic value of observation it will be 1 by J rho R prime O R.
The average value of the expectation and the number, the expectation. Now it is defined as trace of density matrix times the observation.
So this is the space.
না সেটা ঠিক আছে, তাহলে আমি সেই ডেনসিটি অপারেট একটা অবজারভেবল হচ্ছে e টু দি পাওয়ার মাইনাস বিটা এইচ হলো, আর ওটা
O is the operator.
O is operator of observation.
সেখানেও আপনি ট্রেস নিচ্ছেন, ওখানেও
No. This Z is trace of e to the power minus beta is, and this rho is e to the power minus beta is. 1 by Z. Yeah. So 1 by Z, rho is e to the power minus beta is, and then operator. And if we apply this formula, so we can okay, our job is to find expectation value of Hamilton. Our main aspect is to find expectation value of Hamilton. So I can express this way. So this is the so this is the Hamiltonian. So make it numerically doable. We just divided. We got considered some number of paths, capital N number of paths. We have considered capital N number of paths, and here we have considered each path like this. Here. Each path we have to call S, and each path and the sum of all the paths.
So this is basically the incident pattern of the action.
Yes.
Divide action.
Yes. No.
Your device action. And this is the incident expression of the activity.
Yes, exactly. So this is the we have considered m number of paths. We cannot consider all the paths because we are doing numerical. So we have considered capital N number of paths, and there is time integration. We have just considered m time integration. We divide the time path into m prime number of small intervals. So delta tau is tau by m prime, and tau is the temperature. Remember, tau is 1 by temperature. So tau is temperature, and this is the kinetic energy. This is the kinetic for I. This is the total energy for I part. This is the energy for I part. This is the energy for I part. So this is the time interval, the I part. So I and J. I is the path index, and J is the time step. So time has been discretized. So J is the time step. So this is the time derivative basically, kinetic energy, and this is the interaction. Okay, so there should be confinement potential also. So we have considered confinement potential, interaction, and the okay. This we include all these potentials, confinement potential and interaction potential. This we contains all the potential. And this U contains the same J, but delta t times, because there is integration of what delta tau, that will on delta t is this. So delta t multiplies. Integration is dt times that is this. And how to choose the path using this formula. This is our formula. And overall, and using this probability, our final Metropolis algorithm becomes, it becomes 1 by m prime. This is kinetic energy, this is potential energy. So this is the our final. This is so I can implement this in our computer. So I can find energy. We can implement this in our computer. We can find energy. And okay, there is, and this is very, we need to, this is competition very heavy. There are some techniques to reduce the computational power. So I'm not going to discuss this. I'm just telling the result. So we using that formula we get this result. This is the energy per particle unit of astronometer, and this is 1 by 10 power. So this is the energy versus temperature. If you get energy versus temperature, you can find many things from this card, the specific heat, and you can see statistical book. You can do. So that's it.
Even increase the temperature, the energy, you increase the temperature.
So this is the high temperature. This is high temperature. At high temperature, particle will be high state. So
let's see, increase the energy.
Decrease the temperature.
From this background, one cannot conclude that.
Actually, I have to say, sir asked me last week, and I have not prepared for anything. So I have choose this. This is not. This work has not been done. We have choose for PhD program. One of my students is here. He joined 2 weeks late earlier, and I choose this problem for him. So this is the formalism of the problem, and I have not tested all these things. So I have to share this formalism with you so that I can get feedback from you. Because my sir is here. So if I give some mistakes, so you may catch me.
Ajay,
Whatever I am talking, so he teach me. So if you get any mistake there, so you can catch it. You will explain.
To show the condensation, to show that at unlike 10%, the energy should be average energy, average finite is.
Okay, this is not this is the whole energy, not the energy. Because some items are I told you the you say conspiracy equation is considered only downstream particles quantity. In this system, not only the downstream, all the particles. So if we apply the equation of this to that, we can separate the number of how many particles are in the downstream and how many particles are in the external. And you can, there is many opportunities. So on only this method can apply some, but if we compare these two methods, there is many opportunities.
Is there any possibility that cannot act like the analysis to study the average maybe that not the potential?
Actually, I have not tried it, so I don't have vast idea. So this is our starting of journey, not the end of journey. So there is no result. So this is report has been produced by one of my master's students last year. So I have not think seriously about it because we are starting now. Let's say So I'll consider your point why do you have this?
আলফাটা হচ্ছে ভ্যারিয়েশনাল প্যারামিটার।
Yes.
ওকে,
So for uh, yeah.
হ্যাঁ, এবারে ফাইনালি এই ভ্যারিয়েশনাল প্যারামিটার গুলো আপনার মানে অ্যালগোরিদমের মধ্যে কোথায় আছে সেটা একটু মানে আপনি
Algorithm তো-
আপনি কি ওই প্যারামিটার গুলোকে টিউন করছেন?
হ্যাঁ হ্যাঁ প্রথমে আমি একটা মানে আলফা বলে একটা চুজ করলাম, চুজ করে ইনার্জিটা বের করলাম, তারপরে অন্য একটা
মানে আলফাটা যে চুজ করছেন ওটা র্যান্ডামলি কোনো অ্যালগোরিদম ইউজ করে?
no 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 কোনো অ্যালগরিদম না, that random based on the actually previous result, or we may consider the so
He's looking for data. It's
energy.
হ্যাঁ সেটাই, মানে আলফাটা চুজ করছে কি
এবার চুজটা সিস্টেম হিসেবে করা যায়,
and it is researching.
basically তাই researching. And okay, so alpha actually this alpha will start from see if we consider this potential, so I know the solution, construct solution of this potential
দ্যাট ইজ গাউসিয়ান টাইপ।
Gaussian. So this alpha may be very close to that.
আচ্ছা,
So we start from this point and go slightly. I mean, randomly choosing, but with some change. That's no systemic.
থ্যাংক ইউ।
Any question?
Sir, for the final thought, what inferences can you draw about? What is the final inference of this? Very last.
These are. This is just we have calculated energy as function of temperature. And statistical mechanics, this is very important. Energy as a function of temperature. From there, you can find the thermodynamic quantity like specific heat and some other quantity, some other quantity. That's the important.
For theta, then there is 9 per